And we're back. Let's sort it out together. This is O snap. In this problem, we have a ball on a string, and we can measure the radius of the circle that will be swept out when we swing this ball around. And we want to know how fast can we do that before the string can't take it anymore and snaps, and then the ball will no longer be moving in a circle. So the force of tension is going to increase as we increase the speed of the ball until we get to the breaking strength of the rope, then it would snap. So we can think about it, if the centripetal force required for the ball to keep moving in a circle is greater than the breaking strength of the string, then it will break. So we can set those two equal to each other. Let's find that point where they are the same. So then plug in for that, centripetal force mv squared over r, breaking strength is given to you in the problem. Rearrange for the velocity, and that's the expression we can use for that. So that'll tell us how fast we can be going, but we want this as a rate of rotation in RPM, revolutions per minute. So one way to think about it is to do this. In circular motion, the velocity is given by the distance divided by the time, and in circular motion, the distance is the circumference of the circle, and the time is the period, which is the time to go around once in seconds. So that's our velocity. Let's rearrange that for the time. So the time to go around once would be 2 pi r over v. Then there's a related concept called the frequency, and that is the number of cycles per second. And the frequency and the period are reciprocals of each other, as we wrote out here. That means that the expression we wrote above, we can interchange top and bottom. So actually the frequency would be given by this, the velocity divided by the circumference. You can go ahead and plug in what we found in the first step for v, if you like. Then that is going to be the frequency in revolutions per second, but we wanted revolutions per minute. So our final step would be to take this result, and then we have cycles per second. So in order to convert that correctly, let's put seconds on the top and minutes on the bottom of this fraction. Then we'll see that we need to multiply by 60 to get it into revolutions per minute. There you go.